Could you please record? Great.
Thank you.
Thank you.
Thank you. So I will try to share my screen and give you an idea. Okay. Let me find share. Yes, it's here. Okay. So let me make a very brief introduction. Okay. To random access memories. So random access memories are basically two terminal devices. Okay, as you will see from all the presenters, they can be realized in many different options. So in our group, we have developed a technology working with silicon nitride as a resistive material. Here you can see the material. Okay, and one of the electrodes that we are using is heavily doped silicon. This material has very nice characteristics in terms of variability in set and reset voltages. Okay, they exhibit very nice neuromorphic behavior, so we can simulate neuronal synapses very easily. And the big advantage of ReRAM technology, as you can see also in the next talks, is not only the memory application, okay, but is the many different unconventional computing approaches that you can realize with them. One of these is neuromorphic computing. Another one is what we call in-memory computing. Okay, you can make also different logic applications using memristive. Yes. Okay, and also you can realize very interesting devices taking into account if you try to utilize the noise that is created by these devices, and you can realize two random number generators. So, and the big advantage is that since it is a two-terminal device, they can be organized very easily in crossbar arrays. Okay. This just as a very brief introduction to ReRAMs, okay? And now I would like to present the authors, the speakers, okay? So we have
Sorry, could you please mute your microphones?
Or Panagiotis, maybe you can have the access to mute to everybody.
Yes, I will. Yeah, okay. So it's my pleasure today, okay, to present the speakers for this today digital school. So we have Dr. Konstantinos Rogodakis from Hellenic Mediterranean University. Then we will continue with Ashyal Kachadiev from Unova. We will make a break for 1 hour. Then we will continue with Samir Kumar Malik. And we will close the digital school with the lecture from Rizil Thomas from AMO in Germany. Okay, so this is the agenda of today's meeting, and it's my pleasure to give the floor to Konstantinos Rogodakis and start his lecture. Please, Konstantinos.
Thank you very much, Panagiotis. We should just confirm that you can see the slides in a full mode. Full screen?
Yes, you can see. Yeah.
Okay. So thank you very much for the introduction. I know that our colleagues in Athens, they are working on, let's say, silicon-based microelectronics technology, microelectronics, conventional inorganic semiconductors. In our case here in Hellenic Mediterranean University, the focus of the lab is printing technologies. So the main activity the last 10 years during our participation in graphene flagship was solar cells and solar modules and the indoor and outdoor characterization using mixed halide perovskites. So this was the initial point. And since a few years ago, we have developed also expand the activities to print electronics beyond solar cells and specifically on memristive devices, as Panos mentioned previously. So more or less, we are using the same structure, so a solar cell structure, using halide perovskites as the active layer. And apart from solar energy harvesting, of course, we have shown that we can use the devices as memristive devices, and also we can tune the properties and the configuration and demonstrate both non-volatile memristors suitable for artificial synapses, but also volatile memristors that more or less can be used to emulate neuron activity like in our brains. So today I will try to summarize our activities focusing on this topic. Here are some funding sources that we have. Most of them are European. Of course, one of them is INFRACHIP that organizes the event today. Very briefly, a few words about our lab. So we are located in South Greece, here in Crete, the island of Crete, and specifically Heraklion. As you can see here, the solar irradiance of the region, and specifically in Crete, is very high. So it's the best place, one of the best places to evaluate and develop solar cells and modules and panels. So this is the main activity of the lab. But as we discussed before, we have some other, let's say, research directions. One is to develop inks using 2D materials like graphene and other related materials. So then we use these inks and integrate them in our solar cells that are mainly perovskites or organic, and both at small scale but also at large scale. We have printing upscaling facilities to fabricate modules and even panels that I will show you very briefly later. And the last pillar is what we call printed electronics. That includes the memristors that we discuss today. So the goal here is to develop electronic circuits from one hand for the Internet of Things activities, and on the other side, we have to provide power for all these IoT electronics. So these activities are merging. So we combine solar energy or other forms of energy harvesters together with printed electronics in order to develop electronics for the IoT, or in general for the Industry 4 or 5 applications. Very briefly about the facilities of our group that also are available through INFRACHIP. I guess that most of you are familiar with INFRACHIP, so all the partners of INFRACHIP consortium offer their facilities to everybody in Europe and outside Europe with free of charge access. And so our lab can provide facilities from material formulation here at the bottom of the pyramid. Also, we can fabricate at lab scale. When we say lab scale, we mean a few centimeters square, but also upscale devices, mainly photovoltaics, but also printed electronics like memristors, transistors, sensors, using 2D materials and beyond. Some examples of the manufacturing facilities: we have glove boxes and chemical hoods for the material preparation. We have a separate lab for characterization, both for photovoltaics, but also for electronics, for accelerated aging tests, for example, this ISOs chamber, for probe stations, AFMs, and many other equipment. This is the upscaling lab. As I told you, we can go at large area of printing with screen printers, a mini roll-to-roll system, Dr. Blade and other facilities. Another important area of the lab is the outdoor measurements of solar cell solar modules technologies. So we have a specific solar farm. We call it Open Air Lab. Here we install, of course, commercial technologies, but also research-based results like the perovskite technology that I told you before. So this is one photo from the first solar farm in the world using perovskite panels. So these 9 panels are the first in worldwide using the technology of perovskites and 2D materials integrated across the structure. Okay, just to close the overview. So the last 10 years, we participated in graphene flagship. So we are developing 2D materials, and we integrated 2D material interlayers of dopants using 2D materials across typical solar cell structure, either doping the perovskite or forming an interlayer between the active layer and the transport layers. So the result was this integration helped us to improve the efficiency, the power conversion efficiency, but also most importantly, the stability, the lifetime stability of the solar cells and the module. Okay, very briefly here, we have a series of applications with our colleagues in the last, let's say, 5-6 years. One example was bismuth telluride flakes or nanosheets that were integrated as a dopant of PCBM, that is the electron transport layer, and also as a barrier between the silver pad here and the active layer. So both of these approaches allow us to increase the efficiency and the stability of the devices. And this is the highlight of, let's say, the group and the graphene flagship participation in graphene flagship, publication in Nature Energy on the cover, big collaboration between many partners of graphene flagship. So here we demonstrate the first solar farm, as I told you, with quite good performance for at least 9 months until lamination failure here of the panels led to degradation of the PV panels performance. Just very briefly, so in this very big effort, we and our colleagues here, we formulate the materials, fabricate, prepare the inks, realize the modules, the cells and the modules, and 9 panels total. So we speak about more than 3,000 solar cells integrated in 9 panels. So as also I mentioned before, one activity is the energy harvesting activities, mainly on PV technologies, but also we have a team here that develop emerging harvesters. When we say emerging harvesters, we mean devices that can convert mechanical strain to electricity or moisture to electricity or even thermal energy to electricity. And the goal is to fabricate, to integrate these devices in wearables. So to achieve a self-powered operation of these wearables and IoT sensors. The main activity here is develop 2D materials that can allow us to develop these harvesters as a parallel activity to the solar cells and solar modules activity. Okay, so here how these activities are, let's say, synchronized. From one side, okay, everybody now has smartphones, smart devices in our houses. Everything is smart, from our TV, from our fridge to everything. So all these IoT devices they require power supply. So one option is to integrate the energy harvesters beyond PVs in order to provide the power supply for these smart systems. And of course, all these billions of devices require also data processing. And one solution to avoid this huge energy consumption for data processing is to go beyond von Neumann architectures. So neuromorphic-based systems, like what we are doing here with memristors, is one approach to minimize the required power for big data processing of all these IoT devices. Okay, I think that I should not be very technical in this presentation, it will be generic. So I have an introduction about the fundamentals of memristors or resistive switching memories, as Panos mentioned before. Then a small introduction to why we use printing technologies as compared to conventional silicon microelectronics technologies in clean room, etc. Then I will show you very briefly some examples of our memristive solar cells. So this device can harvest energy, but when you need to process data, you can use it as a memristor. So we can emulate artificial synapses and, with non-volatile devices, but also quite recently we developed volatile memristors, so we can emulate firing processes like neurons are doing. And then some examples of how we improve our devices in terms of stability. So in this work here, we integrated 2D perovskites on top of our 3D perovskites. And this allows us to improve the stability of the devices and the performance. And in this study, we replace some expensive materials in our system to achieve a more sustainable, let's say, performance. And in the last section, if I have time, a few words about our volatile memristors. So in the previous work, we are using lead-based perovskites. So lead-based mixed halide perovskites allow us to achieve much higher power conversion efficiency if we speak about solar cells. So we started our activities using our standard solar cells that contain lead. However, of course, we need to avoid lead if we want to achieve, let's say, applications in wearables, etc. So we have developed lead-free perovskites quite recently that allow us to implement both non-volatile and volatile memristors. However, the efficiency here, as we understand, is lower than lead-based systems, but the important here is not so much the efficiency, but this multifunctional operation of the devices. So, just to summarize here, on the right, we have the first papers of the lab using, as I told you, lead-based memristive solar cells, but quite recently, we demonstrate also lead-free based memristive solar cells. So what is the goal here? The goal here is to, as Panos mentioned before, in a real, let's say, processor, you need a crossbar array with many nodes. So here, each node, each red, let's say, point here is the active layer of the memristor. But keep in mind that these nodes here are at the same time solar cells and also memristive devices. So the concept here that we propose is that we can have a flexible, of course, we speak about printable devices, so we can print the device on a flexible substrate or even stretchable substrate. The maximum temperature here, manufacturing temperature is 150 degrees or less for the annealing of the perovskite. So in principle, it can be done at very low temperature. So the manufacturing cost is very low compared to silicon-based technologies. We don't need any complex, let's say, room like the clean room, microelectronics. We don't need a very complex equipment. So it's a very cheap approach that can be on flexible substrates. Of course, our devices are not so highly performing as conventional silicon resistive memories, but for the IoT applications, the sustainability and the low cost maybe it's more important compared to high computation performance. So in any case, so we speak about solar cells, memristive solar cells, so we can tune the resistance of the devices of course, by electric fields, but also by light illumination. So here we have 2 degrees of freedom. We can tune the state either by electric pulses, but also by light pulses. So I will show you our, let's say, reference device, how it operates as a solar cell and as a memristor, some synaptic functionalities, some light tunability. Then how we integrate 2D perovskites for enhanced durability. Then how we replace expensive materials with cheaper one to improve more the sustainability. And the last part will be our recent results on lead-free perovskite as a, let's say, a greener approach compared to lead-based system. So why we need membristors? Okay, standard von Neumann architectures, you may already know, you have a separate CPU and a separate memory unit in our standard processors. So this has some problems. We have this memory goal. We have to transfer data between the processor and the memory. We have this heat goal, the Moore's law. So these hurdles of conventional von Neumann architecture. So one option is to go beyond von Neumann. One example is this, what we call in-memory computation or bio-inspired computation, what we call neuromorphics. So these systems can perform computation and data storage at the same node, so we don't need to transfer data. And also, in principle, the power consumption of these operations is much lower compared to von Neumann architecture. So we can open the path for big data, for the IoT, and all this ChatGPT, this, for example, ChatGPT consumes, I don't know, megawatts for a simple operation. So on the other hand, our brain consumes only 20 watts. So the goal here is to mimic the operation, the architecture of the brain, and minimize the energy consumption for these emerging applications, IoT, AI, and all this stuff. So the other element here is the optoelectronic control. Our devices, as I told you, are solar cells, so they are tunable by light. So in a typical optoelectronic memristor, like this example here, you can tune the resistance state by modulating the light illumination. We are doing also the same. So it's another degree of freedom for the operation of the device. So before we continue, the question here is, can a solar cell also be at the same time a memristive device? So this started a few years ago by Professor Lira Cantu group in ICN2 in Spain. So demonstrate a solar transistor, they call it. Actually, it was an OPV, organic solar cell with a ferroelectric layer integrated, and they have shown that they can control the current through the device, of course by light, but also by changing the polarization of the ferroelectric material. So it was like a solar cell that can also be a type of memristor or solaristor, as they named this device a few years ago. However, the ferroelectric material required a very high temperature to form 500 degrees or more, and the switching voltage for the ferroelectric polarization was more than 10 volts. So these are not compatible with low temperature processing, so flexible substrates, and low power operation. I will show you how we continue this work. So few words very briefly about the memristors, resistive switching memories. So memristive device or neuromorphics, let's say, in principle can have a high data retention. They can be scaled down. They can offer also high data density storage. They can consume a very low power per switching event, and can be quite fast on the nanosecond range. The drawbacks are they have a high variability and high cost, and also the endurance is cycling endurance not very high. However, this memristors can open the path for many applications like cryptography, in sensor computing, and as we discussed, logic in memory or processing in memory computation and neuromorphic computation. Few words about the main KPIs. Okay, the device in principle has two different resistance states. We call them, the first is the high resistance state and the other is the low resistance state. Of course, we can have intermediate states in between, depending on the device. We have a standard set voltage. Maybe I can go down to see the graph. So here in the typical IV characteristic, the device starts at high resistance. When we exceed the threshold, the device jumps to a low resistance state. So this is the current, this is the voltage. And then the device stays at low resistance until you exceed the threshold, the other polarity, in order to set the sample again, reset the sample to high resistance. So it's a typical Arrow switching of a memristive device. There are also some types of memristors with a gradual switching. Here you see we don't have an upward transition, but a more gradual. These two types are associated, at least for perovskite community, to two different modes. So the upward is related to a filament formation. So actually we have a conductive path between the electrodes of the memristor. So that's why we have this upward transition, while the gradual switching is associated to the accumulation of charges at the interface, not a filament formation. That's why the switching is not very abrupt. Okay, for the terminology, we have the set voltage, reset voltage. Then we have the read voltage, where we read the state of the device. For example, usually it's a very low 50 millivolts, something like that. So we apply a positive voltage and then we read the resistance at 50 millivolts. So we will read a high current, so a low resistance state. If we apply minus, let's say, 1, 2 volts, and we read here, then we are going to read the high resistance state. Okay, there are different types. I don't want to share the details. There are the two main types are non-volatile and volatile. As I told you before, non-volatile device, they have a long-term memory. That means that if we remove the bias, the device remembers its state, its resistance state. So it can be used for emulating artificial synapses. And also there are devices that we call volatile memristors. If you see here the curve, if you exceed the threshold, what we call a set voltage, the device jumps to low resistance state, but then when the bias is decreasing, at some point the system will relax spontaneously at the high resistance state. So this device does not have a long-term memory, however, can be used to emulate the firing, some models of our neurons, the firing process, and give us the second element for neuromorphic systems. The first is these synapses, and the second are neurons, in order to implement a crossbar array and a whole system. Okay. Some details here. Now, what are the important key performance indicators? What we call them KPIs. Of course, is the ratio between the low resistance and the high resistance state. The higher the ratio, the better, of course. The second parameter is the switching speed. So how fast we can switch the device between set high resistance and low resistance. Then how much is the cycling endurance, how many times we can go between high and low resistance state. So it's indication for the durability of the device. Then another parameter is the state retention. So if you put the device, for example, at a low resistance state, how many seconds, for example, here, okay, this is endurance, this is retention. So how many seconds can remain there without changing any bias of the device. So this is the retention for the low resistance state, and this is for the high resistance state. Of course, the longer the retention, the better memory device we have. So these are the standard, let's say, measures that we implement to evaluate the performance of the memristors, of the non-volatile memristive devices. So the ratio, the cycling endurance, the state retention, and the switching speed. Of course, in terms of power consumption, we need to be able to switch between low and high resistance with as low as possible voltage pulses. Okay, so these are the main parameters: on-off ratio, cycling endurance, state retention, and switching speed. And the amplitude of the V set and the V reset is also very important. About the mechanism, okay, I told you some details previously. We have two main types, at least for perovskite community. One is the filamentary switching. As I told you, when we apply a high electric field, we have ions and carriers and migration, mainly ions in perovskites, and we have some vacancies that are charged, and these vacancies are conductive. So actually, the filament in perovskite-based systems and maybe in some oxides are the source of the filament formation. The second type of the switching is what we call interface switching. Here we don't have any filament, but we have accumulation of charges at the interfaces and carriers and ions that form a Schottky barrier. So when the Schottky barrier is high, we have a high resistance state. When you reverse the polarity of the voltage, you minimize this Schottky barrier, so you jump to low resistance state. Now, why we propose here solution-based processing for our printable memristors? As I told you, one advantage is the low temperature of manufacturing, the low manufacturing cost, simple equipment. We have published a review paper quite recently about the emerging materials used for emerging memristors. One family is organic-based materials. The second is metal oxides. I think Azal, after me, will speak about oxides. Also, memristors using 2D materials have been investigated a lot. For example, MXCs or TMDs. And the last category is perovskites that is the focus of our lab. So for this kind of printable devices, it's very important the annealing temperature. So this is the limitation, because all the deposition is done at low temperatures, even room temperature. The only demanding point is the annealing of the layer. That should be kept below 200 degrees to be possible to fabricate a device on flexible substrate. And of course, in this paper, we show that each material has advantages and disadvantages. So we implement a benchmarking between the various emerging materials. In terms of maximum memory window, minimum processing temperature, minimum switching voltage, maximum endurance or durability of the membristors. Okay, some details about the printing technologies. So the message here is that a fully printed device should be considered for sustainability. Here, it's important the electrode type. We have to avoid noble metals if we can. So this is the main limitation, that we are still using silver or gold for our contacts, but there are alternatives like graphene or carbon-based paste with quite good conductivity. And of course, we can recycle these electrodes and are much cheaper compared to noble metals. Okay, if it was about the perovskites, this is a typical structure. On the left is mainly lead-based perovskites, mixed halides. We have the cation side A that can be from ruthenium methylammonium, cesium, or rubidium, for example. So it can be either organic or inorganic species. On the B side, we have mainly lead. It's the best performing material, but we have issues with the toxicity. Even the same with tin. And also germanium is used, and the X side is the halides, iodine, bromine, and chloride that have been used. On the right, we have some lead-free approaches that we also use in our lab. So to sum up, perovskite resistive memories, what are the advantages? They have low electric field for the switching, quite good ratio between on and off, so high and low resistance. State retention up to 10,000 or more. Quite good switching, although when we have organic species in the stoichiometry, it's slower than inorganic stoichiometries. They can be solution processed, so low temperature cost, low cost manufacturing cost, can be fabricated on flexible substrates. Of course, we can tune the resistance by light, since the perovskites are photoactive. However, we have to optimize further the cycling endurance. We have to minimize variability, and we have to increase the ambient stability of the perovskite device. Okay, now let's move to some results that we have published the last few years. I don't know how much time I have. Maybe.
You have 5 to 7 minutes.
Only?
Yes.
Okay. So very briefly then. As I told you, we started with the standard solar cell structure. So this is an inverted solar cell structure with mixed halide perovskites, 4 cations as the active layer. A typical IV switching characteristic is shown here. You can see we have a quite good ratio between high and low resistance, 10 to the 5. Set voltage quite low, 200 millivolts, and a reset of 0.8 volts, more or less. We have demonstrated also typical endurance cycles, more than 3,000, and retention characteristics at least 3,000 seconds for some specific configurations. Here, the important point is what about PCE? When we apply all this bias, all these pulses in the device, what about the power conversion efficiency of the device? We have shown that depending on the stress, so if we make DC JV characteristics, PCE is not affected so much. We have a strong suppression of PCE if we send pulses, for example, for endurance evaluation, endurance cycle, but we monitor the PCE on time and we see a recovery after a few minutes. So we don't have any permanent damage of the device, just ions migration upon sending some pulses, but the system is restored after a few minutes. We have demonstrated on the left here, we plot the resistance on time, plug data in dark. So when we increase the light intensity from 0 up to some milliwatts per centimeter square, we can almost analog linearly tune the resistance of the device. So we can do this analog computing, let's say. Of course, we can tune the resistance states also by electrical pulses. Here, for example, we send 2 volts. Here we send 1 volt with a different duration. Typical synaptic protocols, potentiation, process, depression, process. Here we send positive voltages, for example, positive pulses. So we increase the current, while when we reverse polarity, we suppress the current. We can repeat this many. Yes.
May I interrupt you? I'm sorry, I made a mistake when I make the subtraction for the time. Okay, we have 15 minutes, not 5, 15 minutes.
Okay, 15. Okay, slow down a little bit.
I'm sorry.
Okay. Yes, because we started after your introduction. Then, of course, we can tune this potentiation depression protocols with light illumination, plug The blue data are here in black, in dark configuration, while when we increase light illumination, we can tune the conductivity. Also, we demonstrate other protocols like short-term plasticity, long-term plasticity, PPF, and other types of plasticity. This is another work with our colleague Joanna Milic she is in Finland. Okay, we have a 3D perovskite. So we thought, okay, what about putting a capping layer on top? Specifically a layer, 2D layered material, perovskite capping layer. So Giovanna provided to us two different types, woodless and copper type of 2D perovskites and Dion Jacobson. Okay, we tell them here, name them BNA and PDMA. And then we wanted to see if this passivation layer is going to improve mainly the stability, but also affect the performance of the memristors. Okay, we implemented X-ray and wide-angle X-ray scattering in the wax in order to identify what we have deposited on top of our perovskites, and we indicate. So this X-ray curves here indicated that we have a low-dimensional phase that is formed, a quasi-2D, let's say, phase on top of our 3D perovskites. So this is heterostructure. Then we built fabricated devices, reference devices, and of course devices with BNA and with the second type, the PDMA 2D perovskite as a capping layer. And then we tuned the thickness of this capping layer through controlling the concentration of the solution that we deposit on top. And we found the best conditions, the best, let's say, thickness for these two different capping layers. And for the best thickness, we fabricated many devices, at least 30. This is the reference devices. This is 30 devices with BNA, and then 30 devices, at least 30 with a PDMA. And we extract all the statistics of the devices, and we monitor the set voltage, for example, compared to the reference device, and also the variability through this CV parameter. So what we call variation coefficient, CV parameter, that is actually the ratio between the standard deviation and the median values for each data set. And we identify that devices with the capping layers have both lower CV parameters, so let's say lower variability. So we improve the reproducibility of our devices, and also the set voltage for the targeted materials are lower compared to reference. So this was one improvement. Then also we monitor the endurance and the state retention, control, and then type A and type B. Type B, so FBNA, actually was found the best, the most stable. We demonstrated more than 5,000 endurance cycles with no very small degradation, let's say, compared to reference, we see it's much more stable. And then we monitor the device lifetime stability. For this, in the first row here, we kept the devices, as I say here, in the box under the atmosphere, and we measure them periodically. And then we put them again back in the box. In the second row here, we have another test. We put the device outside in ambient air without encapsulation, and we monitor again the performance of the device. So to be brief, here again, devices with the capping layers, the 2D perovskites on top, show the better stability, especially BNA retained their performance even after 40 days outside the box without encapsulation, giving us the highest ratio compared to the control and to the other 2D capping layer. So the last, before go to lead-free, so in this work, actually we wanted to replace one of the expensive materials of the structure. So this is usually we use PTAA, which that is quite expensive, and we replace this layer with SAM. with self-assembly monolayers that are very cheap. And we wanted to see how the performance will change by replacing PTAA, that's a very expensive polymer, compared to the simple SAM layer. So just very briefly, here are the data. On the left are for the PTA devices, on the right are for the SAM-based devices and the comparison. And the result here is that some devices exhibit lower set voltage, slightly lower set voltage, and also the variability here, distribution of set voltages was lower compared to PTAA. So this was an improvement. And also in terms of cycling endurance and stability tests, again, some devices were better than the reference PTA device. So we gained both in terms of sustainability, but also a small improvement in terms of performance. Now, what about, okay, I showed you a lot of results on non-volatile memristors for synapses. What about neuron emulation? So for this, we need a volatile memristor. So I decided to change the formulation to remove lead from our system and to move to lead-free configuration. So this led to the first publication for our group here a few months ago. So we demonstrated volatile switching or threshold resistive switching using inorganic lead-free perovskites based on cesium and bismuth. I will show you later. And then using these volatile memristors to demonstrate some protocols for neuron activity. Okay. In this stoichiometry here, we tested both silver and gold as paths. In both systems, we managed to have a volatile memristive behavior, non-volatile. That was another goal. However, here is again the manufacturing process is very, very simple. Again, a typical inverted PIN solar cell structure. These are the standard, let's say, volatile IV characteristics. You can see that when we remove the bias here, the device always stays at the high resistance state. So this is the volatile type. Then we send some pulses with extended duration. This was a 3-second pulse. And then we monitor the current. We observe a firing process at the end of the pulse. But then when we remove the pulse, the system very fastly dropped to high resistance state. So it was, let's say, a quick diffusion back to the high resistance state. A typical endurance, cycling endurance curve is shown here on the right, at least 700 cycles with a good, let's say, transition between high and low resistance. Then we try to emulate some leaking integrate and fire protocol. This is the standard, let's say, the best protocol for neuron emulation in the community, what we call LEAF. So you send various voltage pulses with different amplitude or different frequency. So you implement either amplitude modulation or frequency modulation in order to activate a firing process. Also, we emulate potentiation and depression protocols. This is the comparison between amplitude and width or pulse width modulation. Here, when the pulse amplitude was low, so 2 or 3 volts, we didn't record any current, spike current. Only when we increase the amplitude to 4 volts, after a period of time, we monitor a current spike in the system. Then we kept the voltage amplitude constant to 2 volts, and we changed the duration of the pulse, and we observed that only at above 50 milliseconds as the duration of the pulse, we can monitor some pulses, some spikes, current spikes, and the effect is stronger when the duration of the pulse was 100 milliseconds. Okay, then we wanted also to achieve a non-volatile lead-free based memory, so that's why we changed again the stoichiometry. We put some silver inside our system. Then we found that when silver pad is used, we can have a non-volatile memristive operation, while when we have gold as a pad, we have volatile memristive. So with the same structure, I mean, in terms of perovskite and the other layers, only by changing the electrotype, we can tune between non-volatile and volatile memristive. So this is the configuration. We also changed the structure. Now it's a normal. So this is ETL, perovskite, HTL, and then the top electrode, and ITO is the transparent electrode on the bottom. So typical non-volatile curves are shown on the left with silver-based and volatile with gold-based on the right. We demonstrated typical threshold behavior for the gold-based electrodes, threshold behavior by changing the amplitude of the pulses. Then for the silver-based non-volatile memristive, typical synaptic protocols, PVF index, long-term potentiation depression, spiking time-dependent plasticity, and spike rate-dependent plasticity already demonstrated using these devices. As a final, let's say, application, we also extract some parameters from the experiment, and we insert these parameters in neural net simulation. We use this for classification of niche database with quite good accuracy for non-volatile devices, mainly. I don't have time to explain these results, but we also are doing similar activities using transistor configuration. So this is a 3-terminal device. We have some applications already. Here, we can control the resistance of the device by light, by drain bias, but also by gate. So it's another flexibility that allows us to transistor configuration to implement. Okay, I can skip this. Also some modeling work. We can develop some algorithms for binary classification using gain parameters extracted by our experimental devices. In this work, we use a lot of data collected from transistors, memristive transistors, in order to build a database for pattern recognition. So we have built a tool here in the lab. So now we have trained the model with a lot of experimental data, and now the model can recognize the different types of curves that we usually measure in our devices, and can classify the device, for example, if this is a good memristor, or this is a bad memristor, and also can give us a feedback why, for example, these devices are better than the others. So we have a closed feedback loop between experiment and neural net modeling to improve our device. Just to close my talk, as a lab here, we participate in 2 big research infrastructures. One is Immerse that unfortunately is finishing now, but we may have a second round. It's similar to INFRACHIP, but this infrastructure is only for printed electronics. Everybody now knows about INFRACHIP. So our school is a part of INFRACHIP. Just to finish here, within INFRACHIP, we published a white paper, some key members of the consortium about INFRACHIP mission. So one of them, we analyze the goals of INFRACHIP and in general this research field. One of the potential, targets will be these flexible hybrid chips. So the goal is to develop some flexible platforms or wearables or other applications that integrate both rigid or semi-rigid or thin the graded circuits together with flexible printed components at the same chip, and optimize this, how we call them, hybrid chips. And we benchmark this hybrid approach compared to rigid, semi-flexible, or fully flexible devices. So to finish, I would like to thank our team here with Professor Kimakis, who is the main PI of the group, and a list of colleagues that participate in all these publications, and of course our funding sources in Europe and in Greece that support our experiments and our research. So thank you for your attention.
Thank you, Konstantinos, for this very comprehensive and interesting presentation. So I would like to ask all the participants to raise their hands, okay, by pressing the icon in Zoom in order to see if there are any questions. Okay, so please let me, Konstantinos, make a question. What is the difference between, I mean, in the mechanism for to discriminate the non-volatile and volatile type of memristive behavior?
Yes.
It is just the endurance, or it is different? It is just the retention of the mechanism, or there is a different mechanism?
Yes, nice question. If you check here the schematic, so the different how we switch to non-volatile, we put a silver pad on top. So we believe during evaporation and afterwards, silver diffuses inside the active layer and allow us to form, let's say, a stronger filament. That's why it gives us this non-volatile behavior. On the other hand, when we have gold pad, gold is not very active, so we don't have any diffusion. That's why devices using gold are only volatile. So it's a different mechanism. We believe that we have a participation of silver migration inside that give us this non-volatile switching.
Okay, very nice. Thank you. Well, since I don't see any raised hand, I would like to ask. Let's move to the next presentation.
Sorry, Panos, there is a question in the chat box.
Oh, yes. I'm sorry.
Yes.
Yes, there is a question. So Pranjal Sharma is asking what are some primary things to keep in mind when fabricating solution processed ink for devices?
Yes, if I understood well, it's about the quality of the inks that we are producing and using them for the printing technologies. Yes, it's very complicated topic. So inks should be stable. So especially when we speak about 2D material-based inks, you have to carefully tune the solvent, the concentration of the material inside, because if you exceed some threshold, the ink will collapse in few hours. So then you cannot use it, or you make some aggregations. So it's a very complicated procedure, but we have a separate team, chemists that optimize the solvent, the concentration. Another approach is also to include some surfactants inside to improve the stability of the ink in time. I mean, to be usable after, let's say, weeks or months without any aggregation or degradation. But this is a very important direction for all the printing devices.
Okay, thank you. So let's move to the next speaker. So I would like to invite Asal Kazadeh from Uninova to take the floor, okay, and start the presentation. So,
Hi, good morning. Thank you, Panos. So I'll start to share my presentation.
Welcome.
All right. Good morning, everybody. Today, I would like to talk about flexible electronics and our technology currently, like at CENIMAT, thin film transistor, and also resistive switching devices and combination, and showing one small block also to you. But before that, I actually like to show you a brief introduction to this electronic industry that in the past we had like a lot of random devices working, like have different functionality and different like separated devices. And nowadays, all of them all actually like we don't have these different nodes, but we have everything function at the same time in, like, for example, one phone or other gadgets. And then future goes to having like Internet of Things, smart cities, a smart house. And, this means like a lot of data is going to be transferred, a lot of different devices and concepts are supposed to be built. And then the quality of life, hopefully, is going to be very much improved. And it's like another level of actually human intelligence, in fact. So looking at all of these paradigms and new technologies, so we can see that how much this data, actually, the transfer, shuffling the data and having all the computation is getting every time like more and more. And we can see the amount of, not regarding just the amount of data, but also the processing and the computation. Does it have any carbon footprint? Of course it is, especially with nowadays energy-intensive language models like ChatGPT, Alexa, Siri, and all the time also developments in this regard. So after this brief introduction that I'm sure like perhaps Kostas also talked about it and you're aware of it because of media and so on, and I would like to talk a little bit about what is the bottleneck and why we have such an actually huge carbon footprint in this regard, which is called von Neumann bottleneck. I just comment that von Neumann is a great scientist and engineer, and actually their current computing system has there would be no problem if it wouldn't have this amount of actually data shuffling. But nowadays we really need to think of a non-von Neumann structure, which doesn't mean that von Neumann didn't do a great job. So if we look at a von Neumann paradigm or a structure in the computer, so as soon as like you turn on your PC, so it loads data from ROM, loads basic input output, and then operating system and so on, and then from the hard drive into the RAM, and all this processing happens. And then when you're starting to start to work, there is always the data bus shuffling between the CPU, the central processing unit, and to the memory. And if we would like to just assume this distance, if you look at like this board, for example, here, so, and assume that the transistor of 40 nanometer size, so this is like a distance of 4 centimeters, so 1,000,000 times larger than the size of a single transistor, and it is equivalent to a human walking 1,000 kilometers to fetch data forth and back. So then you can actually understand better what is this von Neumann bottleneck. And as this AI market growth is happening, as we can see here like a global market of artificial intelligence technologies and all of these smart devices, where we are now, it is going to be even further away, like in an exponential growth, as it is shown actually in this graph. So this means like we are constantly like increasing this carbon footprint just because of this 80% of time and power, which is consumed exactly in this data shuffling between processor and all the time to the memory unit. So, and then we are creating lots of clouds. And as you know, also especially after COVID time, there was like a lot of people were held in the houses and working on lines, and even we started to need more cloud, more data centers, and then millions of news in this regard. And also scientifically, as you also perhaps you know about the MIT news, like was I think 3 years ago, that showing that training a single AI model can emit as much carbon as 5 cars in their lifetime. So this deep learning has a terrible carbon footprint. And here you can see this is the world's energy production, and this is where we are. So we are actually accelerating to even exceed and like take over this world energy production. So we need really market dynamics, limited scenarios, other paradigms to really overcome such a challenge here. So in this, to solve the problem and look at it from a different angle, so we can say, so we have the von Neumann architecture and CMOS technology currently like everywhere, right, that we are using, that has, as I showed, there is a latency and also privacy issues, even because you send everything, like including, for example, medical data, you send it also into the cloud, and then the privacy issues can be arised. And then it has huge power consumption, and then also scaling limits. Also, we are approaching to restriction of the scaling limits. So this is a modern age AI, which is nowadays, and there is a next generation AI, which are scientists or thinking like a non-von Neumann paradigms and a different way of computation and processing, which means that it works like brain, like how brain actually does the job. So using very low energy, like 40 watts for many tasks at the same time. So it is not just the cognitive tasks, even is lower energy, but it's really low energy. It's a real-time data analysis. So the paradigm should follow exactly these kind of characteristics. It should have in-memory computation, memory-centric computation. No data shuffle should happen between the processing unit and the memory unit, and should be power efficient system, exactly like brain, and biological synapses, and then high density information at the same time. So this is so-called neuromorphic computation, where we have like neurons, but electrical neurons mimicking exactly like a biological neurons and synapses. And then we need to go towards these sort of paradigms. In this regard, I would like to introduce a memory store device that currently, like since a decade, accelerating. Actually, the technology is now reaching to some level of actually maturity. And I would like just to introduce what is the memory store. Since I missed Costa's presentation during an early meeting, I'm not sure actually if he introduced. I hope that it's not boring for you. So a memory store can be understood as a fast, non-volatile unit. So it is like, it works like a synapse. So it is a smallest and simplest synapse structure that we can in fact build. So, and at the same time, you can even use resistive switching phenomena as neurons. I don't have the neuron property here, but rather a synaptic property, meaning that if you have a continuous training of the pulses here, right, electrical pulses, which can be translated exactly as the pulses or signals that we receive in our nerve system. So you can change it from the high resistance state, which is HRS here, to low resistance state. And it is like mimicking like a plasticity of the synapse. So the conduction, which is equivalent to the synaptic weight here, as we want to translate everything like from biology to the electronic like perception. So can increase and decrease, and it's so-called potentiation and depression. Usually the behavior is like this exponential behavior as it is shown. So if we look at the state of the art, the fastest switching speed reported is 50 picosecond and so far, and the smallest unit of the memory store is actually very small, like in the range of 4 nanometers square, so can be engineered. And this is a device that perhaps can be used for the neuromorphic computation, where we need really artificial synapses and we need to work on a different computation paradigm. So here in this slide, I try to show you actually what we would like to make in the hardware. Like this is a ANN like architecture that software and computer engineers actually use to solve problems, but based on the software, which is again following the same carbon footprints, because you send your data to the cloud, to the processor, and then all this happens inside an architecture, which is a von Neumann architecture. And what we want to do, we would like to actually kind of emulate the same thing exists in software on the hardware. So for any paths and any connections and any nodes we need, we require a certain hardware here. So here you can see a neuron and like a biological neuron, and the mathematical function of that. The first thing we need to understand is like, so this exists in biology, and then what is the mathematical function of that? That is like, there are many signals coming from these dendrites, like there are many signals are entering there, and which the W is showing like the synaptic rates, and the sum of these synaptic rates makes the neuron to fire. So this is what we do need. And this is here on the right side, you can see this is a normal, like a neural network, artificial neural network. So you have a certain input layer you define based on your features. So there are certain intermediate layer that performs computation, and you adjust. So with these lines, you adjust the weights, the synaptic weights, to reach to a certain output layer, and then build your like classifier, or this can be trained. For example, in the software, you train it and then you use it as an inference. And this is what I am trying to explain in the later on the software. So looking at this, so for example, here, the core functionality of this is matrix vector multiplication. So this is how actually it works. To recognize, for example, the image, to say that if it is a triangle or if it is not a triangle. So, and then you adjust these weights with a lot of training data. And then afterwards, when you use, so based on this adjustment, which is called training, so you can actually recognize and classify different type of data sets. So now we would like to have a physical system directly mapping the AI algorithm. So there comes the memory store device, which in the single unit, you can adjust the resistance states of this device. So this is a mathematical matrix, for example, and this is a hardware, electrical. So on each junction, on the middle, you have a small resistive switching device or a memory store, which the conductance can be changed based on the voltage you apply to this line. So these are all in the crossbars, and usually to solve this vector matrix multiplication, so you have the input vector of the voltage here, and then you have certain conductance of each like resistive switching devices, and afterwards based on the Ohm's law, like the Ohm's law VI, and then Kirchhoff's law on the column, we can actually have for each array of the matrix, we can actually have these certain crossbars, and then implement exactly what exists in the software on the physical mapping of the AI. So as it is shown here, so the Ohm's law and then Kirchhoff's law on each column. So it looks simple, it looks doable. However, there are challenges of this hardware. When we talk about software, everything can happen inside the code. So you can actually tune the code, optimize it very well. But talking about hardware, it means immense challenges. For example, these are the 4 challenges that I actually have it from one of the simulator. It is called like the cross sim that is mentioned here. There are even more challenges when you go to the system level, like to the circuit level. For example, on the device level, conductance variability. So the memory store, it's not a mature technology yet. So we would have certain variability between device to device. Some nonlinearity challenges of this memory store. So it's not actually very linear response. As I showed by the train of the pulses, you can have this very nonlinear response. conductance noise, the unique signature, like a challenge in the electrical devices, and then the drift. So you store the resistance here, but for how long? So there should be the certain, for each paradigm of the hardware we use. So we need a certain, this is called retention time. So, and we need to study this conduction drift of the single device. So after this brief introduction, I would actually right now go inside to the flexible electronics, what we do in our center, like since like 18 to 20 years. And using all of these paradigms and showing you some examples of, in fact, the resistive switching devices together with TFT and using the vector matrix multiplication. The motivation and our objective is like we use thin film transistor based on indium gallium zinc oxide, which is commonly used in display markets, so conventionally available. So the technology is from Japan, as perhaps you may know. And if I talk about the oxide quality, so this material has very good mobility. They can be transparent. We can have a uniform actually layer of this IGZO, this amorphous oxide semiconductor. And it can be low cost and also processed at low temperature, which means we can actually have the flexible substrates and use this technology on flexible. So cheap and large scale manufacturing is possible. So our motivation is there are a lot of disruptive also application that can be targeted in wearable technology, for example, healthcare application, smart packaging, item tracking, and so on. So that's why we focus on this material. And then at the same time, if briefly I talk about the physical mechanism behind this material inside the thin film transistor. So I would like actually to introduce this paper that I really enjoyed. It is in 2018, and it was written by Hosono to write about this IGZO transistor, which is very nice historically and also scientifically explained in this article. And then briefly talking about the material, for example, the presence of the indium due to having these large 5s orbitals, it gives high mobility because of this overlap of these large orbitals. So there is no restriction, and they can have a very good mobility. So giving this property to the material. Look, for example, the gallium here, it makes a stronger bonds with the oxygen more than like indium or zinc. So then it can restrict the oxygen vacancy generation, which at some point, this oxygen vacancy, for example, on the thin film transistor should be restricted. So we need a certain property of the channel material of the transistor. However, if we use the same material, for example, for another electrical device, like a resistive switching based on IGZO, then it should be engineered differently. The presence of the zinc, so these elements I am explaining, it's also inside just thin film transistor, not inside the resistive switching. The zinc, for example, stabilizes the amorphous structure and it prevents the indium oxide crystallization. So talking about the mechanism of this material. So it has trap limited conduction. It is in the trap limited conduction mode. And then up to the certain threshold voltage, which is shown like here, it is one of our typical transfer characteristics of the transistor. Then it starts to have a percolation conduct, to go to percolation conduction mode, and then which is dependent to the V on, the threshold voltage of the transistor. Usually the transistor have a very large on-off ratio, as we can see here. And this is a typical output characteristics of devices that we use. And we can have different structures, like a coplanar one, a staggered one, and top and bottom gate, depending on different applications. And As I said, so these devices were used in display application. For example, let's start looking at 2012. It was on a smartphone, small tablets. And then by moving to 2015, already the film could be produced on large TVs and then also like activate the pixel, as you can see here. So this is a single pixel circuit of the AMOLED here, and there is an address transistor here, and then driving the LEDs, and it has a very high mobility. So in display technology, there should be an ability to form a thin homogeneous film on a large size substrate, for example, using this amorphous material. There should be a dramatic increase in electric current at a low gate voltage when you subject this thin film to the voltage of the gate. So in the display, there are these requirements. However, if we are going to think of using the same material, for example, in computation, then we don't need actually a homogeneous largest size thin film, because on CPU they are, but we need a very pure and nice and repeatable actually unit. So there are other certain things that needs to come to the picture depending on the application. Here, I am just having two examples of our resistive switching. The thin film transistor work started with our scientist Pedro Barquinha here in the center years ago, and showing like just this paper from our center. So currently we have different types of a structure, again, depending on what we are going to be used. For example, if we want to have low overlap capacitance, then we go to this coplanar structure, or if you can see also the figure of merits are different. For example, if we go very low in the channel length, we are also optimizing it, and hopefully soon with nano imprint, we can reach even to the smaller channel to have a better subthreshold swing like for the transistor. But as you can see in the table, you can have good mobility or bad mobility regarding like what actually you're targeting to use. So currently we have the IGZO, and the gate dielectric is aluminum oxide. And usually we use the molybdenum as drain and source and the gate. And then we can have encapsulation of aluminum oxide, or for example, for compatible being of the transistor to use in certain biological application, we can also use parylene C as an encapsulation layer. Looking at this transistor, I should mention that the TFT are just N-types. So if you would like to use it in the periphery circuit, so the circuit is getting larger, but with certain application, for example, if you're targeting a variable, for example, using this for certain detection on the masks, for example, gas sensing, you want to combine this, like I am just giving you some example, like the resistive switching, the transistor in the periphery. So you have a large area. So that's why if the circuit becomes a bit larger, maybe you wouldn't care because of, again, depending on the application. Talking about the model, so there are various models existing, like the conventional power law or MOSFET model is usually used for this transistor. However, the best model is a ChemCast model from the Cambridge. It is a unified model, so you can model the linear region and then the saturation, like if you look at these output characteristics with using only one single function, which is not in power law, we cannot do that. And at the same time, when we use a MOSFET model, we use a threshold voltage, which is a drawback for our transistor, and in this model is modified by using only V on obtained from the semi-log current of the transfer curve. And then also the mobility in the MOSFET model is, we know that the mobility is the gate voltage dependent, and it varies, and sometimes it gives certain non-accurate actually results, and here is also fixed here. But this model, comparable to the power law model, this is not a physical model, so it's an empirical, but we have certain empirical numbers that you can see in the full functions of this IDS SAT and IDS lead. That is the G0, kappa, and alpha. These are empirical parameters that can be extracted from the transfer characteristics. And then we, besides that, so we have a smoothness parameter to describe this transition from the linear, looking at this output characteristics to the saturation region. And then also we rectify and modify the model based on the contact resistance of the transistor. So this is a nice model that can be transferred to Verilog and can be used then afterwards in the circuit. So going from the TFT, so looking at TFTs, I should say that they have a very low leakage current. This can be very advantage, especially for applications in AI hardware, because there is a big demand to reduce power consumption there. And then power consumption means, so all the circuits and systems are like we do use pulses, right? And when they are in the standby mode, means like with this low off current, we actually do not consume large power. And this can be used in any, like on the edge device, which is doing the computation itself on the, like on the Mac processing, like multiply, accumulate, exactly this matrix vector multiplication that I explained. And from like the clock, for example, the frequency of clock, of course, like you have certain moments that the device is off, and this standby power can be really, really extremely reduced. As I have one just example of this IGZO transistor and the CMOS transistor here, and you can see how low we can actually have the leakage current. In this example, the channel is very small. It's like this is a structure that is shown here. So this is like a 21 nanometer. So, and this shows the extremely low off current, and the authors claims this is because of they purify the gases are like hydrogen, the material from hydrogen. So I would say that hydrogen has an extreme role in this composition of amorphous oxide semiconductor. In one hand, for example, for the transistor, we need to purify this gases like and have low level of hydrogen to have a better channel material and very low off current. On the other hand, if you want to target, for example, optoelectronic application, we actually need to dope it. So then we have certain amount of OH group or the oxygen vacancy. I will show it in coming slides, and then you can have another functionality in another novel electronic device, which is called optoelectronic resistive switch. So looking at this extremely low off state of this transistor, one can say these transistors actually are suitable for memory applications. So here I try actually to convince you like why we are using amorphous oxide semiconductor resistive switching. So by now we have very good transistors. We have very nice low off current. So why not using the same material to build resistive switching? So then we can have everything from periphery addressing and so on one system, like for system on panel applications, low cost, and at the same time, not interfacing between different technologies, right? So first of all, the film conductivity can be controlled over 8 orders of magnitude. So this needs certain engineering for having a good resistive switching device. So this is like where we are actually going to change the composition here. For example, the same composition of indium gallium zinc cannot be used for a resistive switching device. So it should be certain changes to actually have certain amount of oxygen vacancies working there as a filament, or I will show as this area dependent resistive switching. So the technology can be used exactly, again, why I'm just emphasizing, because we have a TFTs, we have this mature technology in this place, so we can actually use the TFTs on top of each resistive switching as an address transistor. So this is an advantage because of, again, low interfacing between the different technology. So this is an access device for each resistive switching. So we decrease in total lithography mask count, so cost reduction, low temperature processing, then it can be suitable for flexible electronics. So because everything share the same technology, methodology, and fab. So low power circuit operation because of having this low of current. So here I have an example of one of the transistor in the structure of the crossbar, which has this resistive switching and then transistor as an access transistor here. So as you can see here, depending on the current of resistive switching, on the right side, I have an example of the resistive switching. Depending on the current, because we want to drive resistive switching, like not like display driving the OLED or access transistor there, but driving the resistive switching. So we need to tune it based on the current level of resistive switching. So you can see the aspect ratio of transistor is large if the current is large. So this is one of the, let us call, I don't know, drawback or something more challenging, like, okay, we need to reduce the current of resistive switching to have smaller transistor to be actually to address the device. Here I show a typical memristor or resistive switching device based on amorphous oxide semiconductor, and this is IGZO device. And I show here that we have actually area dependency. So meaning that these devices, in fact, don't work like filamentary ones. In the resistive switching, we can have, like based on the amorphous oxide semiconductor, we in fact can tune it to have it filamentary, resistive switching, or area dependent. So just giving you an introduction, when you build an MIM device, like a resistive switching device, actually, we don't build it in the fab. We make it afterwards based on the electroforming. So you have a certain device similar to MIM, and then afterwards you do electroforming, which is a large ones, just large big voltage to form the filament, and after that time you can call it resistive switching device. So the pristine device is has a potential to be a resistive switching device, but it's not itself, like after fab, a resistive switching. And then this is usually it is non-volatile switching. You can tune it to the certain level of the resistance states, and normally the resistance change is abrupt. So the set is when you are applying voltage to go to on state of device, low resistance state, and then reset is when you're coming back to the off state and the device. So of course, it's not like just one filament, you can have multiple filaments and so on. So in amorphous oxide semiconductor, we observed that if we change the polarity, for example, in the case of zinc tin oxide that we published this in 2019, we observed that if we change the polarity of resistive switching, we can change it from one filamentary mode to the area-dependent resistive switching. So here in the area-dependent, so set happens on the other side of the like a voltage polarity, and then reset on positive. So, and at the same time, we notice, so we call it analog resistive switching, gradual change of resistance, and this is abrupt, which is non-volatile resistive switching. So the advantage of the area dependent is it is forming free. So you don't need that large special like voltage that you apply and you create a filament. It has a very low device to device variation, very low cycle to cycle variations. However, it has poor retention time. We noticed that in many actually devices, we use noble metal because of just the presence of the oxygen and how the working mechanism actually is presented in the resistive switching device. We noticed that if we exchange the platinum with molybdenum, we can actually have the same material as our transistors, like when gate and drain and source electrodes, the same material, the same electrodes, and at the same time, we can again duplicate the same resistive switching properties, analog, gradual change of resistance state, and area-dependent device, as it is shown in this figure. So you can have a very nice analog behavior based on changing the current state in the set
or stop reset voltage. So stop the voltage of the reset at different points, and you can and the different resistance states can be achieved. And the property on top that I am showing is more for the abrupt one with the non-volatile property, and then certain variation between cycle to cycle and device to device. So in order to improve retention time, so we have lots of advantages, but still a certain disadvantage for artificial neural network paradigms, like to use these devices, to train these devices, for example, and to keep the resistant states. In order to improve that, so we need actually to know the mechanism. So we believe it's a change of Schottky profile barrier that is happening during set and reset, and then giving more pronounced tunnel current or less pronounced tunnel current during set and reset accordingly. So if we want to suppress this charge exchange, so we can actually, it is based on the papers from Jülich, from the group of the Professor Regina Dittmann, we learned that we can actually apply a small layer of aluminum oxide. This is in collaboration with Jülich. And this way, we can, in fact, improve the retention time. It's not still fully, so I have the figures of retention time with the tau decay that we did with the fitting here. That is like better, of course, in this case. It is still ongoing because of the quality of aluminum oxide, how it is deposited, and then also it should be very, very little. So now we are testing actually between two centers. This is an ongoing work, and testing this layer and to further improve the device. So when the aluminum oxide is like 2 nanometer, you still keep this area-dependent resistive switching phenomena. However, when it is very large, like 3 nanometer, not very large, but slightly higher, then you start to have abrupt resistive switching because aluminum oxide is insulating and you need to break it actually via forming. For ANN approach, so usually, like what we need, it's like we need a linear and symmetric weight update, like synaptic weight update. So meaning that you have a certain pulse numbers, and then the conductance needs to change based on this pulse number, which are completely equal pulses. And you have this change to potentiation and then depression. This is the ideal scenario, which I have it on the left side. So to use crossbar as vector matrix multipliers, so we need to reach to this ideal scenario. And this was like the studies that happened some years ago, actually, like in all the community of resistive switching. So people tried, for example, I have some examples here for you. If you have identical spikes, which is ideal because you can do training, so you can actually work with this device. So on this specific device in the literature, they showed that they have potentiation with this trend of increase and then suddenly abrupt depression. So it's not actually very ideal. So they changed it to non-ideal spikes, like increase the amplitude of the spikes, and then all right, fairly, they are reaching to this linear and symmetric weight update by changing just the pulse width, which is the last scenario. So if we want to use these devices, so this is like just our neural network, our system we talk. So there is an input layer for each column. You need one crossbar, right? That column 1, and then another one for these hidden layers in the middle. So based on the number of the nodes, you need to define your size of the crossbars. And then on this should act actually ideally linear and symmetric. In this regard, we are looking at our IGZO device, IGZO resistive switching as an active layer here, and the molybdenum top and bottom contact. So if we use identical pulses here for potentiation and depression, we see that we have this exponential change. We change the amplitude of the voltage, as you can see in this figure, and also the time, like 500 microsecond. So here is like the time of the pulses, and you can see this is the real scenario as we have. So potentiation, depression, exponentially, however, device to device and cycle to cycle variation, this is 50 cycles, is very, very low, but it's still exponential. So we would like to tune or engineer it. Then we started a very nice study actually together with Maria Pereira, my former PhD student, who is now a successful scientist in this regard right now. So we start to have pulse scheme modulation. So starting to have different pulse scheme. For example, incremental amplitude of the pulses, and then incremental width. So we change the width of the pulses, and then at the end we started to have another paradigm, the incremental amplitude and width, and we see, all right, if we change the width of the pulse, if we change the amplitude of the pulse, we actually can have a very nice linear and symmetric response. And this is nice. So we publish this. And is it feasible to build now a circuit based on that? No, it's not, because if you want to change amplitude and width, so every time you want to adjust the weight, you need another memory system, another one human system to remember, right? So this is achievable, but it's not feasible when you look at it at a system level. However, so this is what actually we achieved, and we show that this is possible to tune really the devices. So we have, and at the same time, very low cycle-to-cycle variability. Nowadays, by the work of IBM, just I believe like it was a year ago, was published by a group of IBM, we can relax out a little bit on this linearity and symmetric, and using tiki-taka algorithm, so you can keep certain like exponential behavior of this response, and using a certain algorithm to fine-tune it and do a nice vector matrix multiplication there. And this is a very nice study shown, and this means a bit like a nice point for hardware people, because we need to implement what exists in software, and sometimes we really have certain obstacles, but nowadays we can really relax out. So with this consideration, we made the first proof of concept using the the amorphous oxide semiconductor transistor and the resistive switching in the units of 1T, 1R here. So, and you can see there is a shared node between resistive switching and the transistor, and then with the source line and the word line is connected to the gate, which acts as a compliance, and we can actually have different levels of the gate, different levels of the channel. And then since our resistive switching is current controlled, so you can have different current level and control different resistance states here. And here is a typical plasticity characteristic showing potentiation and depression of our devices. And then we examine this device using a simulator that is called a cross-sim simulation, is capable for the deep neural network application. And then, I'm sorry, for deep neural network application, for pattern recognition, we use MNIST handwritten digits here, and examine both in this regard exponential and also the linear response to see the difference accuracy. So this is a software benchmark, as you can see, and here also we could examine the impact of nonlinearity of devices, asymmetry, the cycle-to-cycle variability, and even noise. That also we published. The noise level of the area-dependent device is extremely low, however, like especially random telegram noise compared to the filamentary devices. Then as a proof of concept, we built for an array size of 4 times 4, like 16 elements. And then we show here with adding a transistor to each cell of resistive switching, we solve the sneak path, so there is no crosstalks between the units. And then we also show the simple vector matrix multiplication using the voltage vectors in here. And additionally, we implemented the same system on the flexible substrate and showing the proof of concept that it works because it's a low temperature processing. And then we did certain bending tests, and then we observed that it can be reliable to the certain bending tests and can be still functionalized. All right, so I showed that the area-dependent devices actually are volatile RMs. So we didn't discard these devices. For example, we have a lot of devices showing certain volatile behavior. By now, we talked about just the hardware that needs a certain retention time to actually be realized. And here, we are using the volatile RMs in certain tests to see if they can be implemented in the physical reservoir computing, which is, if you look at this paradigm, so it's like a black box. So it's much simpler. It is used for temporal data processing, which is nice because these devices are suitable for flexible substrate, and you can implement it in certain variables or certain sensing nodes that used in variables, for example, for ECG, EEG, and so on, that are you deal with the temporal data. So this is a nice paradigm to follow. And then in physical reservoir, you don't need a very large and rigid structure, as I showed before. So here, the work and the I would say the birth of physical reservoir computing was with nanoparticles, that using nanoparticles network. And then what we are trying to use, we use actually the crossbars here, the better controls, and in terms of scalability, I would say. So for a device to work in physical reservoir computing, you need to have certain criteria. First is fading memory, showing short-term memory to long-term memory with the train of pulsing, nonlinearity, and high dimensionality. So this is the first test we did. We tried, this is a zinc tin oxide device, so we don't use just HZO. We also moved to the greener technology, use only zinc tin oxide here, and then we fabricated a small crossbar here, and then we started to have a different stimulate of the pulses and see the improvement of the current, and then at the same time, like not improvement, like the increase of the current, and then fading memory actually characteristics here. So devices are completely nonlinear. We started to have pulse sequence responses and different cycle-to-cycle variations. So this means like for each sequence, like we have a certain pulse scheme. For example, one can be introduced as a pulse of -3 volts, for example, to our devices with a certain length, and then there is a read as 0.1. So then you change different sequences and you are dealing with different actually signature of these devices. We checked also the cycle-to-cycle variation, the device-to-device variation of the device. And then we started to use, with collaboration with Gianluca Milano from INRIM, we actually started to use to benchmark our devices for pattern recognition using MNIST data sets. This is a very common data set and common tasks to be used. However, this system is good to be used for temporal data. Currently, we are starting to use gas sensing, gas data gathering, some like to benchmark really this network with the temporal data. You can use also certain function like microglass function to induce the temporal data. So, but this is a very first level of showing if the system works, which is like a static, like MNIST data. And then it's like we binarized it, right, the data, and then we start to actually benchmark our device. And this is showing the overall performance of the classifier in this confusion matrix here. We notice that we can optimize our device into 5 bits, which is very nice in terms of the training parameters. So we had a reduction of 28% training parameters, super power efficient, with only 1.8% drop in accuracy. So, And here you can see it's like 91, around 92 like accuracy, which is still good for certain applications, and especially when you're dealing with the temporal data, like a forecast and so on. So currently we publish this work together with Emmanuel Carlos on the printed. So we are not just working on the vacuum process devices. This is a device that is printed, and we use the zinc oxide resistive switching device here. This device has silver electrode. As soon as you see silver electrode, so the device is a CB RAM, a conductive bridge RAM device. So it has this certain signature of the resistive switching IV curve here. This is printed, and then we started to combine this with the transistor here that comes actually from kit. This is an electrolyte based transistor. This is a ongoing work. And then for this part of actually this we show in our recent that is going to be available soon in advanced intelligence systems. So we show the capability of this device also to be used as physical reservoir computing. And we try to see if, because it is different. If you want to have a good retention time, so you need to deal with a different pulse scheme and different controlling, right, of the resistive switching. Again, up to certain point, this device has a nice retention time that can be used. If you want to use the same device in a different paradigm, then you need to have a different methodology. So our target is like how to use this device together, of course, with the transistors, like printed ones, and reach to a full system. This work can be also realized. This is also in an elegance project, European project led by Kostas, and which is a very promising project with a very nice, large consortium. So not just using the volatile resistive switching, the same material for physical reservoir, we are also, especially talking about elegance, we use this material at the same time for optoelectronic applications to work with to build neuromorphic vision sensors. So we need certain optoelectronic synaptic devices that can be activated by light, right? So there is certain drawback in, again, this the same as data. So traditional image sensors, you need to fill pixels and then fixed frame rate gathering of data from all pixels, even empty pixels. So this is not very power efficient system. How if we build a sensing system, a neuromorphic sensing that just capture the movement, right? So as a very continuous flow of data. So each pixel is activated when there is a movement, right? And independently, it records when it's triggered by this movement. And then this can be realized for pre-processing of the image, for example, the edge enhancement, contrast correlation in a very, very power efficient system. This image, like the concept is shown here, that we actually would like to use the same system as in brain, in the eye, like I can have it. So we capture certain like a light from different objects, and how we are processing in brain, we are going to realize it on the circuit. So for the very first level of understanding this circuit, we need to understand the device. So one device, possible and potential device, is the IGZ optoelectronic resistive switching. This device is a vacuum process. And again, talking about hydrogen, as I mentioned before in the slides, here we need hydrogen. We need to dope the active material here by hydrogen to create certain subgap states which can be activated by visible light, because IGZO band gap is around like 3.05 electron volts. So it can be activated, so you can target it, like you can have this electron transfer with UV light. So if you would like to have a RGB recognition and sensing, so we need really to have this doping system. And then, as you can see here, this is a normal IGZO resistive switching and hydrogen doped, and you have we can have increased on-off ratio of light, and you can see in the transmittance that how this IGZO actually starts to absorb here. In this device, as a proof of concept, we have a very thin layer of gold here that is still kind of, it can be, okay, it's not transparent contact electrode, but can pass the light. Here is very, very thin layer of the gold. And then we started to test the device based on using the optical set. So we use the green light here and blue light, and here is like the UV. Unfortunately, still we don't have red activation. This is ongoing on this device, that how we can have maybe double layer structure, how we can have different doping mechanism to actually activate this device with red light. And you can see that it has certain like selectivity to different lights, and also to different intensity of light. And then it has this PPC, persistent photoconductivity, so-called PPC effect. So it stays. The state can be stayed by light. Recently, we can have it completely non-volatile because we have the double layer. I don't have these results here due to being confidential, and we would like actually to go for the publication, maybe in the next seminar, and or we can have short-term memory to long-term memory. Again, depending on what paradigm we are looking at, we need certain device structure and device performance here. Here we show that it's very low energy consumption using, like, as you can see in these graphs here, around like a femtojoule, very low actually in functionality. And this is kind of the first pattern device, because in most literatures they are all common bottom electrode, and they show a very low cycle to cycle variability, and additionally device to device variations here. So when we downsize the device, in fact, you can see here, this is very advantageous because the off state, the dark period is getting lower, and we can have a better ratio of the dark and bright. So this is our purpose why we did actually this pattern this device. So
Azal, I'm sorry for the interruption, but I think you have 2 minutes to conclude.
Sure. I am concluding. I am very sorry. So here is just a proof of concept of this emulation of the synaptic properties using like a retina base, and we show all of the criteria which is needed for a spiking neural network here, short-term to long-term learning process and post-period facilitation as it is shown, and even a CDP test, which is a core criteria for a spiking neural network. So as conclusion, I hope I could convince you that IGZO resistive switching and beside IGZO TFTs actually can be used for the computation for certain application in flexible technology. I showed you how we improve the retention time for paradigm in an artificial neural network like AI hardware, where we need the retention time here, like deep learning. And then I showed the other actually disruptive applications of using this material and amorphous oxide semiconductor in optoelectronic, resistive RAM, and also physical reservoir computing. So thank you very much for your attention. And this is our group. And of course, engines of this group are always our PhD students who are in blue colors. We have also senior researchers and junior also doctors who are actually in black color. And the session is open for question. And I'm sorry if I talked too much or I gave too much introduction into the topic. So thank you very much.
Thank you, Azal. We have one question in the chat. Okay, it is
Sure.
from Michael Biliatis.
Mm-hmm.
So the question is, can you share one more time the slide with the mathematical model of transistor?
Yes.
And also, if you can use this mathematical model to verify measurements.
Yes. So on the mathematical, this one, right? Unified compact model. Yes, this is what actually we did. These are the real data and the model. And this is the data from our center, like the transistors that we have, subjected to different gates. We can use it, and we use just one unified model, which is presented here. So here you need to actually have all the physical parameters. These are from the data. So you have the transfer curve, you obtain the V on of the transfer curve. You again, like VDS prime, as you can see, there are VDS prime, IDS prime here that they have a certain, so VDS prime is you consider the contact resistance. So you calculate it, you obtain all the physical parameters from the data. Then you also get the empirical parameters, and then you use this unified model. So you have all the parameters ready in different tables. So, and smoothness parameters based on different gate, which is this way it is obtained. This is output characteristics. And you can obtain like this smoothness parameters. It's different for each gate, right? And then afterwards you can reach to really to have to fit your device based on this model. There is huge amount of course, parameter extraction, but we use it and we can have nice results.
Okay, so thank you so much, Azal, for this comprehensive presentation, and also all the speakers, Konstantinos Roldakis also. And we will make a short break for 1 hour, and I hope to see you again at 1 p.m. Okay?
Yeah, thank you very much. Yeah.
Thank you. Thank you.
Yeah. Bye-bye.